So the ideal gas law. We've talked about some simple gas laws, and we can take all of those and combine them into a single law. So for those of you that are interested, this is how it works. The volume was proportional to 1 over the pressure, the inverse of the pressure. Volume was proportional to the temperature in Kelvin, and volume was also proportional to the amount of gas in moles. So we can combine these 3 proportionalities and say that the volume is proportional to the amount of gas in moles times the temperature divided by the pressure. In order to make a proportionality into an equation, you just need to put a constant in there. So the volume is proportional to a constant times those variables. And the constant here is given the symbol R, and is called the ideal gas constant. So we can express this like this with a fraction in it, or more commonly we do it like this, PV equals nRT. And that's what's known as the ideal gas law. So that's an important one to know. PV equals nRT. So R can be R is a constant, but it can be expressed in different units. And just like if you express a length in different units, the number changes. The constant does as well. So the value of R depends on what units we're using for the pressure and the volume. So typically we're going to use atmospheres for pressure and liters for volume. And so that gives R a value of 0.08206. And then the units look pretty messy. Liters times atmospheres divided by moles times Kelvin. And this is a good one to know as well. I'll probably give that to you on that next exam on the information sheet, but it'll save you a lot of time if you don't have to go look it up all the time. Any questions? This is just a slide showing how we can get the different laws from the ideal gas law. I actually don't find that slide terribly helpful. I do want to show you something kind of cool, though. So PV equals nRT. If we take an equality and do the same thing to both sides, it's still equal, right? So if I were to divide both sides by PV, it's still an equality. But PV is equal to nRT. So instead of dividing by PV, I could divide by nRT, and I'm still good, right? Because PV is equal to nRT. So if I have PV is equal to nRT under one set of conditions, under a second set of conditions, the pressure times the volume is still equal to nRT. So I could put subscripts here. I could say P1 V1 is equal to N1 R T1. I'm not going to put a subscript on R because it's a constant, it doesn't change. And I could put subscripts of 2 on the variables down here. So I just took sometimes we call it PivNert. PivNert divided by PivNert. The ideal gas constant is a constant, so it'll cancel itself out. Anything divided by itself is 1. At this point now, you can look at the problem that you're doing and see, well, what's changing? What doesn't change? So let's just say that you had a problem where the pressure and the volume were changing, but the amount of gas and the temperature were staying the same. They don't tell you what the temperature is, but it's staying the same. So T1 is equal to T2. We don't need to know what it is. If they are equal, it's the same number divided by itself, it's equal to 1. If the amount of gas isn't changing, then N1 is equal to N2, and N1 over N2 cancels out. So now I've got P1 V1 over P2 V2 equals a canceled out mess. What's that right side equal to? 1. You cancel everything out, you're left with 1. So therefore, P1 V1 is equal to P2 V2. and there's Boyle's law. You can get Charles' law the same way by just keeping volume and temperature and crossing out the other things. You can get Avogadro's law by keeping volume and N, amount of gas in moles, and crossing out the other things. So memorizing the equations is good, but this, you can derive them very quickly. So you remember PV equals nRT and this little method, and you can get any gas law that you need. Any questions? I think this is cool, but I am a chemistry nerd. Okay, let's use the ideal gas law in a problem. An 8.5 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and PSI of the gas in the tire? So these examples have titles which, give us big hints about what equation we should use. On an exam, there aren't any little hints like that. So you have to look at the problem and decide what kind of equation are we going to need. Now, I showed you in the simple gas laws that it's helpful to make a table and label everything. You can make a table for ideal gas law problems too, and this is really helpful, especially if you're not sure what you're supposed to do. So I'm going to show you how that works here. So we're going to pretend that we don't recognize that this is an ideal gas problem. So we're going to do our regular table thing. We start with the first number, 8.50 liters. And we say, well, that must be volume, because liter is a unit of volume. So I'm going to call this column V. Then it gives me an amount of gas in moles. And so that's N. And then it keeps going, and it says temperature of 305 Kelvin. And I'm thinking, oh, nice. They gave me the temperature in Kelvin so I don't have to convert it. That was thoughtful of them. And now I've run out of numbers, and I have nothing in the second row. That's because nothing's changing. So was this a waste of time? No. I've identified all my variables now. So I don't need the second row, so I'll just get rid of it. I don't even need that. But I have V, N, and T labeled now. If I had a second row with values in there, then I'd have some sort of a changing condition, and I'd need to use a more complicated equation. But nothing's changing here, so this is an ideal gas law problem. PV is equal to nRT. And then we need to remember what R is. R is 0.08206. And the units are liters times atmospheres divided by moles times Kelvin. The units on the ideal gas constant tell us the units that we must use for the other variables. When you're doing simple gas laws where things are changing, we had to use Kelvin for the temperature and moles for amount of gas. But pressure and volume could be in pretty much any unit as long as they agreed, because the units would cancel out. Here, we have to use these particular units. So volume needs to be in liters, check. Amount of gas in moles, check. Temperature in Kelvin, check. Okay, everybody's okay here. We're trying to find the pressure. So we take the ideal gas law and rearrange it first. I don't want to divide by pressure, I want to divide by volume. Rearrange it first instead of doing it after you plug all the numbers in. So the pressure is equal to nRT over V. Now I can put my numbers in. Always, always, always include the units. 0.552 moles is N. Here's R with its messy units. And then the temperature, 305 Kelvin. And then we're going to divide that by the volume, 8.50 liters. Double check the units. So here I have moles, and those will cancel moles in the denominator of that fraction there. And Kelvin will cancel Kelvin. And then I've got liters on top and liters on the bottom, and those are going to cancel out. So the unit that's left is atmospheres. Now I get out my calculator, and I punch this in, 0.552 times 0.08206 times 305 divided by 8.5. How many significant figures should this answer have? 3. All these values that I've been given have 3. This is not an exact number, it's 3 sig figs. My ideal gas constant has 4. And as frequently happens in these sort of book problems, we're going to end up with 3 sig figs. So 1.62, that's my third sig fig, and then I'm going to write down 2 extra digits to avoid rounding errors and write the unit. So rounding that in atmospheres, this is 1.63 atmospheres is the pressure. Are we finished? No, it also wants the pressure in PSI. So this is one of the answers. When I convert to PSI, I want to use the unrounded number. So I'll have to do a little unit conversion here. 1.6253 atmospheres. This I do not expect you to remember, but I will give you the information if needed on an exam. We're going to multiply by PSI and divide by atmospheres. Yeah, it's actually 14.69. I don't like that the book rounded it to 3 sig figs. So it's 14.69 PSI is equal to 1 atmosphere. For pressure unit conversions, we can always do this in one step. So don't try to make it too difficult. It's just a one-step deal. So I've got my 1.6253 times 14.69. This will also have 3 sig figs. 23.876 PSI. And then rounding that will give us 23.9. And that's our second answer. Any questions? So the ideal gas law has 4 variables in it. These problems typically will either give you 3 of the variables or information that you need to find the 3 variables and ask you to calculate the 4th. Yeah, there might be conversions, like they might give you the volume in milliliters instead of liters. They might give you the dimensions of a cube or something, so you have to calculate the volume. Yeah, there's all kinds of fun things. Let's do another problem. This one has some unit conversions in it. So what volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? So we look at this and nothing's changing, so I'm not going to make a table because I'm recognizing now that this is going to be an ideal gas law problem. I still want to organize the information that I'm given. So I've got 0.556 moles. And I know that that's N, the amount of gas in moles, so I'm going to label that. And then they're telling me the pressure is 715 millimeters of mercury. And they're telling me the temperature is 58 degrees Celsius. And then let's write R down here. That's not going to be given in the problem, but we're going to need it. And those units are helpful because they remind us of the units that need to be used. So I've got some unit converting to do, right? What's one that I need to fix? The pressure. So the pressure's in millimeters of mercury. It needs to be in atmospheres. So we'll have to convert that to atmospheres. So we'll multiply by atmospheres, divide by millimeters of mercury. And this is one you should know. 1 atmosphere is 760 millimeters of mercury. That is exact, so that's not going to limit sig figs. So 715 divided by 760. I have 3 sig figs here, 0.940, carry 2 extras. It's important here because this is not an end result. I'm going to use this in a calculation. What's the other unit that has to be converted? Temperature. Gas laws. Always the temperature has to be in Kelvin. So it should be 273.15. The book gets a little sloppy with that. So 331.15 Kelvin is the temperature. When looking at sig figs with temperatures, the best thing to do is just to look at where does my original temperature end? What decimal place? It ends in the ones place. My converted temperature should end in the same decimal place. It should still end in the ones place. Now, we gained a significant figure here. That's okay. We were adding. It happens. Okay, so now we've got our variables. Here's our ideal gas law, PV equals nRT. We're solving for volume, right? So we're going to divide by pressure on both sides. Pressure cancels out. So the volume is equal to nRT over P. So we'll take all of these things and plug them into the equation. So there's N. And here's R. And T is 331.15 Kelvin. I'm going to divide all of that by the volume. No, not the volume, the pressure. We're finding the volume. 0.94078 atmospheres. Check your units. If the units don't cancel out correctly, you made a mistake. Either you didn't convert to the correct unit, or you forgot to convert, or maybe you've got your equation put together incorrectly. So the only unit that doesn't cross out is liters. That's good because liter is a unit of volume. So 0.556 times 0.08206 times 331.15 divided by 0.94078. The number with the smallest number of significant figures has 3, and so our answer should have 3 significant figures. 16.059 liters, rounding to 16.1 liters is the volume. Be sure to do the calculation on your calculator and check me because I do make mistakes, especially on Monday mornings. Any questions? Got to be careful with your algebra. Be careful writing down units and getting the units correctly. The problem itself isn't difficult, but there's just a lot of little places where you could mess something up.